所以说菊花这很不好，一直上。唉，5月1号了，周末，已经第9周过完了，7×5=63，7×5=63，实际上这是第10周了，70天过去了，靠，还剩大概40天。6月12号没完，还是6月11号我是考试，还有第10周、第11周、第12周，我们的课程结束，3周课程结束，3周课程结束，考试估计还得考2周，3+3，3周学习，3周考试。哇，往边坡里看一看啊。Drainage, erosion control, vegetation, concrete, slope to drain, internal erosion, modification of the slope profile. Restraining structure. Miscellaneous. 我讲真，我们那个5505 Project Management 是真他妈的水课，我操！25000去上个这鸡巴课，也不能说它的知识不重要，但只是说啥，它那个东西模棱两可的概念，就跟卡塔尔和那个阿联酋和沙特对巴勒斯坦谁更好？这2个都好，他说了2个都好，没有啥建设性的作用，没用啊！你知道跟不知道，你知道也没法做出结论。哎操，真他妈扯！Lecture to cover. Process for pressure and effective stress distribution. Soft clay and ground coat.垂直排水管加速布局。Surcharging. Vertical tree. Ground coat. shallow foundation.什么鸡巴？
Craters.
10、11、12、3周。Formula sheet for examination. 哎，操你妈 Test 3 exam details. Midterm laboratory. 我操，5月7号要交，我是他妈还没看呢。Not you again. Submission. What exam? Bearing capacity. Topic. Slope stability. Number 1.
This experiment, we are going to investigate the factors which influence the bearing capacity of foundation. The purpose of a foundation or footing is to transfer the loads from superstructure to the soil safely. There are two main modes of failure that occur to a foundation. These are bearing capacity and settlement of the underlying soil.
Settlement.
One of the most famous examples of bearing capacity failure is the Leaning Tower of Pisa. In fact, this is one of those examples where bearing capacity failure did not cause full structure failure. Excessive foundation settlement can also cause to the structural failure. The picture here shown at the bottom of this poster shows a building failure due to excessive differential settlement. So, when a foundation is designed, the engineer needs to know the bearing capacity and the settlement properties of the soil. In addition to these, the restrictions imposed by the geometry of the soil also need to be considered. In today's experiment, we are going to investigate the bearing capacity of footings on sand.
The bearing capacity of the footing on sand. Model footing. Eccentric loading point. Eccentric loading point. Concentric. Factor influencing bearing capacity. Footing geometry. Eccentric loading footing shape. Uniform medium grained sand, losing density.
Factors which influence the bearing capacity will be investigated. These factors are footing geometry, eccentric loading, and footing shape. Firstly, we will examine the influence of footing geometry using three footings with same area but different shapes, and these are a circular, square, and rectangular footings. The model footings which we will be using in our experiment are shown here in figure 1. For investigating the influence of eccentric loading, we will measure the bearing capacity of an eccentrically loaded circular footing. Then we can compare the eccentrically loaded case with the concentrically loaded case and see the influence of eccentric loading. Finally, the effect of shape of footing will be investigated with the fourth narrow rectangular footing. All of these tests will be performed on uniform medium grain sand. Both loose and dense states will be considered. The experimental setup is shown here in figure 2. We have a soil container to prepare this. Sand, a loading frame to apply loads on the footing, and displacement transducer to measure the vertical settlement of the footing. The main steps in the experiment are prepare the sand, place the footing in proper position and install the loading frame. Then attach the displacement transducer to the loading frame, and then we will apply loads on the footing and record the settlement. The objectives of today's experiment are now clear, so let's do the experiment.
Alright everyone, now I'm going to show you guys the setup for our webcast. So what we
你
have
他妈能不能拿个摄像机，别他妈拿个手机，他妈在这凑合，我操！
for the left one, and we're gonna fill this with sand. Using 5 centimeters. Layers like we did for the
你卡你妈呢！我操！
Today's lecture is a new subject area looking at the stability of slopes. Is that screen a bit dark? Not sure what happened to lighting in that. I was going to show you a video just to start off this lecture on slope stability, but it didn't work on the player, so I'll put it onto the website. And there are other videos just showing examples of slope instability. And I suppose the main purpose of showing you such videos is to remind you the fact that there is
等一下，明天我把这个，今天我把这个看一看，明天把报告搞一搞，明天后天2天，明天我把数学搞了，后天大后天，明天后天把这啥给搞掉，周二再把那啥搞 geomechanics。OK。
there are many problems associated with the instability of slopes, and it's a major concern for many areas in geotechnical engineering, and has impacts. It means lots of lives being lost due to slopes being unstable. So it is an important component of any geotechnical engineer. You need to be able to determine why a slope, if a slope is stable, if it's not stable, what you need to do to stabilize it, and how, when you're building your own slopes, how you actually go and design.
Un momento. 看我下学期的课表。Fundamentals of mining engineering。我操！完了，下学期的3门都是恶心课。岩石力学。矿业工程基础，我希望比较基础。Environmental geomechanics， 环境岩土力学，啥他妈玩意儿？啥叫环境土力学？完了，不会又鸡巴有流水啥的吧？我操！第3学期 underground mining, mineral resources, surface mining。冶金。Engineering research project. Mining engineering design. Mine waste. Mining management.哎，我他妈去学个什么 employment relations， 多容易拿分，操！ Introduction to 这个 human resource management， 多带劲 ！Management and organization。
slope so that it will be stable. Now, in terms of, I'm just going to run you through a PowerPoint presentation first. I'm not sure why that screen is. Does that look dark to you on the right hand side? Yeah, I'm not sure what that is. And that's. No, I just wanted to check there. I don't know why that screen seems a bit. You can see it's not as bright as the other one. Anyway, you should be able to see from one of the screens. And the main thing to do with, to remind yourself about a slope failure is usually what is a slope failure?
我靠，25块钱一个，他妈老子买赚了，他妈才8块钱一个，8块还是10块？海南买的。日本品牌装你妈呢！我操，笑死爹了。傻逼，三亚发货，天然深海贝壳，汤匙，三亚旅游纪念品，25块钱一个，牛逼，老子服了。椰子油手工皂，哎，这个有意思。筷子架，海螺，酱料，这个回客。珍珠，那这个店可以加一波收藏。怎么还是中国出口的？我是，我他妈以为我在土耳其买的就是土耳其制造的，还是你妈中国制造，还是便宜。我靠，这玩意儿只有他一家，这个有点夸张了，这么贵，人都带包邮的价格。装个鸡巴破盒，他妈要200块钱，你死不死？18一个，他妈真敢要啊！不要太黑。 垃圾。是真的垃圾，不错，看来我他妈在他妈海南买的这个还真不错，算便宜了。东北那个中年老女的真他妈没坑我，比淘宝买还便宜，不错。你他妈的一个椰子壳，你他妈敢要他妈15块，你怎么不抢呢？这傻逼！
Is that we're gonna compact it with the pneumatic hammer and the blade on top to achieve the band sample, and also to for the loop sample, we're just gonna throw the sand there in the loop plate. We have here our different cooking shapes. We have the square one, the rectangle, the narrow.
你妈的，你没完了！
The rectangle one and the circular one, and for this one we're gonna have
你他妈在这缓冲。
coming down and collapsing. And what is so say what is what gives rise to actually a slope failure? Essentially, it's just the self-weight of the soil is actually causing the slope failure. So the driving force, and I'll come back again on these points, the driving force is the soil weight. Now what prevents something, I mean, what you can see here is there's a component of the weight of the soil here, which is going to push down the soil in this direction here. Now the component, the actual resisting force is the shear strength of the soil. On the failure surface. So in this comparison here, we can imagine the soil is slipping down. This is a so-called, this is a slip surface. The soil is slipping down on that slip surface, and what's actually preventing it from slipping down is actually the soil strength. So if the soil's got a high shear strength, that slipping isn't actually going to take place. If the soil has a very low unit weight, like it's really light material, then the chances of that failure actually are also very low, because the driving force trying to induce that slip failure is very low. So just with that in mind, now I'm just going to run through some PowerPoint slides, just to look at slope stability. Now, slope stability problems can vary in dimensions. They can be very small cases, or in this example here, they can be very, very large. This is a natural slope failure. You can see, this is the slip surface. The soil slid along the surface indicated here, and was 300 meters in length. And you've got to ask yourself, why did that happen? And we'll talk about those issues later on. And this is another large-scale slip, as you can see, where again the slip surface is rolling, is coming down the slope here. This is another one. This is a million tons of material, in this case glacial tail, slipping along that surface there. And one of the most famous examples in Australia is a so-called Thredbo landslide, where because of leaking water from a pipeline, water pressures built up on the slip surface, and because the increase in water pressure reduces the effective stresses and reduces the shear strength of the soil, it initiated a landslide. And this is an example from Australia, but I'm afraid there's far more severe examples from around the world where lots and lots of people's lives have been lost. So it's a major element of geotechnical engineering to try and design against such landslides. And for example, in Hong Kong, especially in Hong Kong Island, where the entire city has been progressively digging into the land, into mountainside, because land has been at such a premium. There's constant issues with slope instability, and geotechnical engineers are very much to the fore in Hong Kong to actually try and come up with ways in which slopes can remain stable, as they are in many other countries around the world. This is just this is an example just from down in Wembley, for example, next to the golf course, which I just took. And this is an example of just a very small scale slip. Nobody cares about this particular slip surface, but it is nonetheless. That's what it looks like after the material has slid. This is the back of the slide and coming down here. And lots of the elements, when you build a road, very often you have to either build up an embankment on which to put the road, or you have to cut into the slope into existing ground. So usually when you're building a road, you want to try and make it as level as possible. So there are areas which are called cuttings, where you actually have to excavate through existing material. And this is an an example of a cutting here, and this is the slope. The slope, you're excavating this area here to construct the road, but this area here, this is a side slope, and you can see in this example here, there's some instability happening. There's a slip failure taking place. That's called a road cutting. You can similarly get side slopes on a road embankments where you're actually building up the level of the road, and again, that's all part of slope failures. You can get minor slips occurring here. You can see this is the top. This is a slip occurring at the top of a road here, and eventually this can progress, as you can see here, to the other side of the road, and the whole slope here can actually fail. So we need to be able to analyze problems like that and make sure that we can design our problems so that you're not going to get that type of failure taking place. So one of the things, on inspection of those landslides from around the world, different examples, there's a tendency to look and you see, for many cases, the slip surface tends to be approximated by a circular slip zone. You can see here, this is a kind of a slip zone. There's the so-called scarp at the back of the slope. The soil is slipping down in this direction here, and this is a slip surface, as shown approximately here, which is it can be approximated in some way by a circular curve, and that's usually what we try and do. We usually approximate our slip surface to be circular, and we approximate it to be circular usually for convenience of solution methods, but also this solution procedure has been shown to be pretty good, and a circular approximation is usually pretty adequate. So when we're actually looking to evaluate whether or not a slope is stable, the first thing we must remember is that we're never going to be able to predict where that slip surface or slip zone is. So what we need to do is assess all possible slip mechanisms. I'll come back to that again in a minute. What we do is we determine what's called the factor of safety of any particular slip zone that we've examined. So what we say, we postulate, we're saying, okay, we're going to get a slip occurring along a particular slip surface. And assuming that that's the slip surface, we then determine the factor of safety against a slip happening on that particular surface. Now, the factor of safety is usually the resisting force divided by the driving force, essentially, and we'll talk about these different variations in terms of factors of safety. But in essence, once the factor of safety is less than 1, it means there's going to be a failure taking place. But the slip surface that gives us the lowest factor of safety is called the critical slip surface. And if that factor is less than 1, it means we're actually getting failure taking place. So if somebody says to you, well, the factor of safety against a slope instability in a given example is say 1.2, it means what they've done is they've examined all possible slip surfaces that can actually possibly occur, and they have found that the one that gives the lowest factor of safety was actually 1.2. Now, if you find that critical slip surface factor of safety is greater than 1, it means your slope is actually stable. However, if it's less than 1, then you've got a failure in your hands. And when you're designing, usually you design so that you've got a factor of safety typically of about 1.3 or 1.4 on the shear strength on the soil.
What did you say?
Two points to apply the load. This one will be the eccentric load in the end. All right, and how we're going to apply the load? We're going to apply the load by this frame here, which has a space so we can put weights here at the bottom.
妈了逼，你卡死吧傻逼！
plates or something like this, we're gonna just
慢慢下来吧傻逼！
Now, if we're looking at a slip circle analysis, now this is again repeating what I've just said in the previous slide. If we can imagine this is a slope here, we're postulating that we're getting a slip occurring along that solid slip circle. And what we do is we work out what the factor of safety is associated with slipping along that particular slip circle. And we define the factor of safety.
哎呦，操你妈！你还让我看不让了？
and he's gonna
缓冲这么久，就缓冲他妈几秒。
apply the load to the
靠你妈！
See, as the shear strength, essentially the shear strength of the soil is what's actually controlling, is preventing that slip from taking place, divided by the imposed shear stress on that slip zone. So you can imagine you've got shear stresses acting on that failure surface here. If those shear stresses are less than the shear strength, then that's good, and it means your factor of safety is going to be greater than 1. If you find the shear stresses on that surface are greater than 1, greater than the shear strength, obviously then it means you're going to get a failure taking place. So you evaluate the factor of safety, as indicated here, for each possible surface. So you need to postulate lots and lots of different circles to actually come up with a solution. This is why the slip circle analysis was the first application of computer engineering in computers in engineering full stop. So since the day of a really long time ago, people with first access to computers, people did slip circle analysis. Basically because you can see that you need to do one analysis with one slip circle. Then you need to do lots and lots more to make sure that you've established what the actual critical slip circle is. That is the slip circle that gives you the minimum factor of safety. So once we've established what the critical circle is, then what I'm saying is that is the factor of safety for that critical circle is the actual factor of safety of that slope. Now the actual for a circular slip, we can look at the what's called rotational equilibrium corresponding to say a slip along the kind of surface I just talked about. So if we imagine or postulate that we're getting a slip along a line indicated here, and we look at the overall rotational equilibrium for that particular situation. Now the shaded area here is the soil involved in the slip failure, and the weight of that particular soil is given the symbol W. Now that weight must act at some location. It acts at the centroid of that shape here, the shaded zone. And let's say that acts at a distance x from the center of the actual circular slip surface, the center of that circular slip surface. So what we've drawn here is we've postulated we've got a slip circle here. To draw that slip circle, we've had to assume a circle center and a circle radius. So there's our circle center, there's our radius, and then we've drawn this circle. Now W, the weight of this soil involved in the slip zone, acts at a distance x from this slip from the center of the slip circle. So now if we look at the equilibrium, the moment about this point about the center of the circle, that value of W times the distance x. So once you have to establish first what the centroid of that shaded zone is first to be able to do that calculation. But again, usually that's done by computers. Because usually you've got an uneven, irregular shape. It's not that clear where the centroid is. But it looks to be at roughly about a distance x here. This is the distance x here. That's roughly where the location of that centroid is. Now that's the disturbing moment of the soil weight about the point of rotation here at the center of the slip circle. The restoring moment arises due to the shearing forces generated on that sliding zone here. Now the actual shear force on that zone is the shear strength times the area of that slip circle. So say the shear strength was tau F, the actual overall length of this here, that needs to be given the symbol AB actually. So there's A and there's B on your notes. It's actually also in there. So the length of AB times one unity into the page times the shear strength, which is a stress. The stress times the area is a force, times the distance from the center of rotation, or is the restoring moment here corresponding to that slip surface. So then we determine the factor of safety, the factor of restoring moment. What we normally do is we say, when we apply a factor of safety, we apply it on the shear strength of the material. So what we say is we've got equilibrium under a factored shear strength, where we've divided the shear strength of the soil, say it was 50 kPa, by a factor of, say, 1.5. So this would be the factored shear stress of the soil on that boundary here. So that's why I've divided here by a factor of safety. And if we equate those two equations, we find an equation for that boundary here. The soil, say it was 50 kPa, by a factor of, say, 1.5. So this would be the factored shear stress of the soil on that boundary here. So that's why I've divided here by a factor of safety. And if we equate the shear strength, where we've divided the shear strength of the soil, say it was 50 kPa, by a factor of, say, 1.5. So this would be the factored shear stress of the soil on that boundary here. So that's why I've divided here by a factor of safety. And if we equate those two equations, we find an equation for the factor of safety of that particular circular slip zone. And that's really all. Once you understand what's indicated on that particular slide, then that's all really you need to understand. That is the basic learning outcome from slope stability analysis. Is you're trying to understand weight is the disturbing force. We're looking at rotational equilibrium here. We're taking moments about the center here. The disturbing moment is W times X. The restoring moment is the shear strength of the soil times the area of that circular slip surface times its distance from the point of rotation R. And that's called rotational equilibrium.
3、4、5、6、7、8、9、10、11、12、13、14。
Two things. If we can show here inside, you'll be able to see that these have a point here where we're gonna put the footing here on top of the sand, and this way we're gonna load the footing. Right?
Fuck you, not right.
And just
now, the shear strength of the soil is absolutely vital to understand those characteristics when you look at slope failure, because as it is in the rest of the course, the soil shear strength governs the behavior of most geotechnical structures, which is why we spent some time on it. But now, from this part of the course onwards, we're going to be looking at mostly applications, and we need to understand how to work out with the shear strength of the soils. I'm going to do a very simple example to start with, just to illustrate to you what kind of slip soil slip in there, sorry. Okay, so the example we're going to look at here, now up to just a second ago, we were talking about all of the failure surfaces in soil being approximated by a circular mechanism. Now, when we've got a very, very long slope, the actual circular mechanism approximates to a straight line. So in other words, if you had a slope that looks like this here, and say it was a very, very long slope,
What do you mean by very long?
the failure mechanism will look a bit like this. Even though it's still circular, it can be approximated as being a planar slope. So this is a failure surface. I'll write down here planar failure surface. So it's true to say that most of the failure surfaces can be approximated by a circle, but if you've got a very long slope like this, you can actually approximate your slope as a planar surface. And what we then do is we zoom in on an element located right in the center of that slope. So what we say here, if we're now looking at this in more detail,
I know this.
we've got our slip surface. Now we're going to call this angle here beta. That's the angle of our slope. If we're looking at this area zoomed in, and we know that this angle here is beta, this is our failure surface, and we're looking at just an element here, the weight of the actual soil is the only force that's really acting, that's driving the slip failure. And we can draw that, we can resolve. I'm just going to draw this first, and then now the reaction of that W force on that here, I'll just call that equal to R. That's the reaction of that force W acting downwards. Okay, so W is equal to R. So that's all we're saying is the actual reaction on that failure surface is equal to the value of W. That's just equilibrium. Now if we actually look at the two components of that reaction, there is a tangential component T and a normal component N. So N is a normal stress, normal force acting on that.
Excuse me. 你妈画错了吧？我操，傻逼！
On that failure surface, and T is the force acting tangentially to that actual failure surface. Now if we call this dimension here equal to 1 meter, and we call this dimension here, just call that height equal to Z. Now what's the value of W in this example? W is equal to
Z.
Unit
Z.
weight is equal to gamma. The actual, if we look at the weight of the material here is equal to gamma times Z. Because this is dimension 1 here, this is a parallelogram, with this is 1 meter, and this is half the sum of the parallel sides times the distance between them. It's basically the volume of that is Z times the unit weight equals gamma. Now if we look again at the geometry of this angle beta is equal to this angle beta here. So you should be able to work that out for yourself, because if you project that on upwards, this is at a right angle here, and this angle here, beta, that's equal to beta, that's equal to 90 minus beta, and therefore that this is the simple geometry. Hopefully, if you don't understand that, have another look, and I can go through with you. So we now resolve this angle here must equal to beta. So we're just going to say W is equal to R here. So T is equal to W times sine beta, and N is equal to W times cosine beta. So we've got a forced triangle here. The resultant reaction to W is equal to the reaction W here. We separated those into the normal and tangential components. T is equal to W sine beta, and N is equal to W times cos beta. Now there, if we now say, well, what is the actual shear strength of the soil on the failure surface? If we've got a dry sand, the shear strength is given by the normal effective stress times the tan phi dash plus C dash. Okay, that's the standard Coulomb equation. C dash is equal to 0, and U is equal to 0. So the shear strength is equal to sigma n dash times, sigma n, because the core pressure is sigma n dash anyway, tan phi dash, because sigma n dash is equal to sigma n. So to work out what the shear strength on that failure surface is, we need to work out what the normal total stress is. Now the normal total stress on the failure surface, and I'll just put some numbers here, just call that AB. The length of AB is equal to 1 divided by the cos of beta. This dimension here, if this horizontal dimension here is 1, this dimension here must equal to 1 over cosine beta. Now the normal stress on AB is equal to N all over the length of AB times 1 into the page, which is equal to W times cos squared beta. Because we've got N over LAB is equal to 1 over cos beta, and W cos beta divided by 1 over cos beta is equal to W cos squared beta. So the normal stress on that plane is equal to AB. That means the shear strength of plane AB is equal to, again, tau F is equal to sigma n times tan phi dash, that's equal to W cos squared theta times the tan of phi dash. Now what's the shear stress? That's equal to W cos squared theta times the tan of phi dash. Now what's the shear stress acting on shear stress on plane AB is equal to, remember now, if we go back to this example here, it's the force T acting downwards on this plane. It's equal to T over the area, which is LAB times 1. That's equal to W times sine beta times cos. Cos beta. W times beta divided by 1 over divided by 1 over cos beta. So in this example here, the factor of safety is equal to the shear strength over the applied shear stress. The shear strength is equal to W times cos squared beta times tan of phi dash divided by the shear stress, which is W sine beta times cos beta. And that's equal to, you can see the cosines cancel here. You'll have a cos beta over sine beta, which is the same as 1 over tan beta. That's equal to tan phi dash over tan beta. That's the factor of safety against a slip occurring along a plane along that
这真鸡巴麻烦。
plane here with length LAB. means is that if the factor of safety here is greater than 1, it means phi dash here will be greater than the slope of the angle. So for example, if the friction angle of your sand was 35 degrees and the side slope of your sand was 30 degrees, then you wouldn't have a failure taking place. If friction angle is equal to your side slope to your sand, then you've got a factor of safety of 1 and you're just on the verge of instability.
Sorry.
Last thing, we have this.
你他妈在玩我呢？
Related sensor here. That in the end, we're gonna put on top of this part. Here to measure the settlements while we apply the loads.
Voila.
All right, everyone. Now I'm gonna show you guys how to.
他妈怎么回事？怎么卡成这个逼样子？我操！
push it here, and remember that we're gonna do 5 centimeter layers. And after that, Yusha is gonna tell you guys how to compact any soil.
你妈，你没完了，我操！
So we are going to compact the first layer.
我不是对的呀，他妈服了。
Similar to your previous lab, so this is the flat board. We are going to put it on top of the there's the pneumatic hammer. So before that, we make sure we wear the earplugs for safety.
Fuck. Здравствуй, Philip with you.
Well, an example of, remember now we're looking at so-called infinite slopes, which are planar, and all we need to do is concentrate in on what's actually happening within this any element here within that plane or failure surface. What we've got here is dry sand, and lots of slope problems arise due to poor pressures within the material, which reduce the shear strength, and therefore we're looking at here in this example of translational slip surface again. It's just drawn the other way around here, just to confuse you. In this example, we've got, again, we're just looking at an element of soil. We've got our length AB here. So the one difference here in this example, again, just to show that there's a bit of variety. In this example, this dimension here is equal to unity. So remember, in the previous example here, I had this distance from there to there equal to unity. But in this example, this distance is taken as unity. It doesn't actually matter. The maths all comes out the same way anyway. But it does mean in this example now, the weight of this particular element is going to be gamma z times cos beta, because the perpendicular distance here is now equal to cos beta. So the weight of that element is gamma z times cos beta. Again, I'll probably just draw this again for your sake here. We use the same. We've got a reaction here, the normal. This is the tangential, and then you've got the resultant reaction here, that W.
不是你往哪边画的？我操！
And what is that? What we've established here is that T is equal to W and sine beta, their forces, and in is equal to W and cos beta. Sorry, this angle here. It is showing you this is theta. So these are forces. T is equal to W sine beta, N is equal to W cos beta. But because we've chosen the length AB here to be unity,
我靠，他妈38了，我操！他妈怎么他妈可40分钟过去了？
it means the shear force is equal to the shear stress. Because the shear force divided by the area is going to be, on this here is going to be W sine beta divided by 1 times 1. So that means the shear stress on that element AB is going to be W times sine beta. And I just write that down just to notate W sine beta all over 1 times 1. And the normal stress on that element is going to be, the total normal stress is equal to N over A. So again, N over A, or N over S is equal to N over LAB times 1, and that's equal to just equal to W times cos beta. Sigma N is equal to N over A is equal to N over LAB times 1, which LAB in this case, the length LAB is equal to 1. I'll just write that down again. Just remind you. So now we want to calculate the normal stress on the base of the element. We've already calculated that normal stress equals W cos beta. The only difference here is we've actually got pore pressure on our solid. So we look at the equation tau F equals sigma n dash times the tan of phi dash plus d dash, and obviously c dash is 0 anyway. Tau F equals sigma n minus u times the tan of phi dash. Now sigma n minus u is equal to W cos beta minus u. So tau F equals W cos beta minus u times the tan of phi dash. So that's the expression here, exactly the same as what we had earlier, but now we've got a pore pressure here of u. So the shear strength of that surface is equal to W cos beta minus u all times tan of friction, tan of phi. So that's what we put in here. This is the shear strength and tau F. So the shear stress, which is causing a disturbance or causing slippage on that plane, is equal to W times sine beta. We've already got that up here. T is equal to W sine beta. The shear stress, we've already talked about that. T is equal to W sine beta. We've established that. Now, we've now got an expression here for the factor of safety being the shear strength divided by the shear stress. So what we've got, this is the expression we've got, and all that's happened here is that it's being manipulated here to this form here. Now we had already our derived, when we had a dry slope, when we didn't have any excess pore pressure, that value of u in that expression equals 0, and you can see that the whole expression then reverts to tan phi over tan beta, which is the same as what we've established already. And we've substituted W is equal to gamma z times cos square beta, and you can, that's here, it's just been substituted cos W gamma z, W is gamma z cos beta, so that means you get U over gamma z cos square beta in this expression here. Now, what we normally do, actually, we'll just revert back a second to this diagram. When we actually measure water pressures, have any of you heard of standpipe? Yeah, so you put a standpipe at a certain location, the water pressure will rise in that standpipe to a level consistent with the pressure at that particular point. So say, for example, we put a standpipe at this location here on the dotted line, which is the slip surface, and say the water pressure at that point was equal to gamma W times H. the actual water in the standpipe would rise a distance equal to h. But sometimes we define and we can rewrite at this point here the water pressure is equal to gamma W times h, whatever height that water rises to. Now, as we see soon, we're going to be looking at different expressions and note in situations where h is not needs to be evaluated separately. So we can also, at the moment probably doesn't make much sense to why we're doing this, but we can also rewrite that expression rewrite the expression for factor of safety by substituting in for u the value saying gamma w times h. So that's what we put in here. That's the same as the value of u there. And that means enables us, as you'll see later on, for us to look at other situations where we need to calculate the value of h before we calculate the value of the factor of safety. So you can see immediately from this here, if you've got a high pore pressure, you're going to have a low factor of safety. And that's one of the major instigators you can see and associated with slope instability. When you start developing water pressures on this slip surface, you can really have a large effect on your overall factor of safety. I'm now going to do a third example, which in this case, just to, and the more practice you get at these better, nearly every single year since applied mechanics was around, there's a question of some form where you need to look at the factor of safety for a translational split surface. So we look at another case now. In this case, we have C dash is not equal to 0, but U equals to 0. So again, it's just some practice in looking at the derivation of these kinds of equations. Now in this example, like the first example, but not the second example, we're choosing this dimension here. We're choosing this is our slip surface. We're choosing 1 here as a dimension in the horizontal direction rather than the direction along the slope. And we're now looking at evaluating the factor of safety corresponding to that slip. So, okay, so everything else is the same as the first example we've looked at, which is this example here we talked about. Exactly the same here, except when we go and calculate what the shear strength of the soil is here, tau f is sigma n times tan phi, we need to add the fact that we've got a C dash component of strength, so we add plus C dash to that component. So in this case, exactly as we had before, A here, I'll just call this dimension A, B, and A is equal to L, A, B times 1. The area of that slip surface along that slip plane is the length of the slip plane LAB times 1. So exactly as we had before, we can resolve n is W cos beta, n over A is equal to W cos squared beta. Now in this case, and T is before is equal to W sine beta. Now we want to calculate the shear strength. We get exactly the same as we had before, except we're adding the C dash component of strength, which is C dash. So now our expression for the factor of safety is exactly as we had before, except now we've got an extra term here equal to C dash. So we got C dash plus W cos squared beta tan phi over this, and you end up with a separate component due to C dash. The second component here is as we had before when we had a dry sand with no C dash. Now we've got an extra component here corresponding to the C dash component of strength.
Señora, 明天早上起来再说吧。洗个澡去。